Hello, my name is Hani El Sabahi. I'm a biopharmaceutical purification application engineering specialist for 3M based in the UK and covering the EMEA region. I'd like to warmly welcome you to this on-demand technology showcase webinar where we'll be looking at some of the results from the work that I've been doing on Biosolve to model bioprocessing costs. In particular, we'll look at how we can disrupt those bioprocess costs using novel bioprocessing solutions. We'll begin the webinar by looking at some key 3M technologies and how those help to make our customers' processes perform better. We'll then look at the processes that I modeled using Biosolve, and then we'll look at the results of the Biosolve modeling. We'll finish off with a summary. So let's take a look at how 3M products can help to make our customers' processes better. The schematic on the top shows a typical monoclonal antibody purification process. So following the bioreactor, you normally have a primary clarification, which can be done by centrifugation or depth filtration, followed by polishing clarification using a depth filter, and then a sterilizing grade membrane. Then it's on to the capture, which is done by protein A chromatography, followed by viral inactivation by low pH hold. That viral inactivation usually causes some turbidity, which is then passed through a depth filter in order to remove that turbidity and the membrane, and then it's onto the polishing chromatography columns. So this is the anion exchange flow-through column and the cation exchange binding loop column, and that's followed by viral filtration. So all of you, I'd imagine, will be very, very familiar with this process. The aim of our technologies is to help to intensify this process by making smaller unit operations that achieve more. Typically, they operate in flow-through mode and take advantage of convective mass transfer. And so the aim is to drive for fewer steps, higher MAB loading on each of those steps, shorter processing times, and very importantly, higher overall DSP yield. So if we apply two of the products that I'm talking about here, which is chromatographic clarification as a single step to the process, and a salt tolerant ST polisher to the process, we can see the impact that it has on the process. So you end up having a shorter process overall. So let's have a look at the two technologies that I mentioned briefly in the last slide. The first that I would like to talk to you about is Harvest RC, which is a single step chromatographic clarification technology. So the aim of this technology is to condense a complicated clarification train like this into a single step that is able to handle the full range of particle sizes and also to deal with soluble impurities during the clarification stage of the process. So essentially, it's a single stage clarification device. For more details on this technology, I would encourage you to listen to one of the on-demand technology showcases by my colleague David Chow on bringing chromatography to cell culture fluid clarification space. The other technology that I'd like to talk to you about is 3M Polisher ST, which is an advanced single-use AEX solution designed to replace the reusable AEX polishing column. This product has a really high MAB loading, so we're talking about 100 times that of a typical Q resin. It's fully scalable from lab to manufacturing scale. It has high salt and low pH tolerance and robust viral clearance across a very wide range of conditions, in addition to viral nanofilter protection. So again, this is essentially bringing improvements to the process by downsizing the size of the polishing column. And again, I would encourage you to listen to the on-demand technology showcase by Joris van der Velde on enabling the transition from column to single-use AEX unit operation for more details on this technology. So let's take a look at how we modeled the impact of the inclusion of these 3M technologies on bioprocessing cost. So these processes were modeled in Biosolve, which is the industry standard for bioprocess cost modeling. We looked at a total of 6 processes, and those are shown here in this schematic. So the first process is a typical monoclonal antibody purification process, so consisting of 2 stages of depth filtration for clarification, followed by a sterilizing grade membrane, then onto protein A chromatography, followed by low pH hold for viral inactivation, and then depth filtration to clear up the turbidity caused by the viral inactivation, and then a membrane to protect the polishing columns, followed by an anion exchange flow through polishing column and a cation exchange binding loop polishing column, and finally viral filtration. In process 2, we looked at swapping out the polishing depth filter for the M-phase AEX hybrid purifier, which is a chromatographic clarification device that is able to deal with soluble and insoluble impurities. So this is removing cellular debris and also host cell protein, and primarily, in fact, host cell DNA. And this has a number of impacts on the process. There are impacts on the protein A column, particularly improvements in the purity post protein A, but also on the cell culture fluid stability. And we see reduced propensity for aggregation of host cell protein and DNA on reduction of the pH. And consequently, post VI, we've removed the depth filter from this process to take account of that. The next process we looked at was further condensing the clarification with 3M Harvest RC, which is the product that I introduced to you a few slides ago. And that again is a single step anion exchange flow through clarification technology. Okay, so this is condensing the 2 clarification steps that we see in processes 1 and 2 into a single clarification step, and addressing soluble as well as insoluble impurities. And consequently, we have similar quality material to process 2 post M-phase AEX hybrid purifier, and therefore there is no depth filtration step post viral inactivation. In process 4, we look at returning to the 2 stages of depth filtration for clarification by implementing 3M Polisher ST, which is able to deal with turbidity, and that's why we don't have a depth filter post viral inactivation or a membrane. So consequently, the 3M Polisher ST helps to condense the process by removing those 2 steps. In process 5, we look at the combination of the M-phase AEX hybrid purifier and Polisher ST in the same process, and in process 6, we look at the implementation of 3M Harvest RC and Polisher ST. And this is really the next generation process that I described a few slides ago. The impact of all of these changes is that you can see with each iteration, the process is essentially getting simpler and simpler until we arrive at the next generation process. So let's have a look now at the impact of those different processes that we modeled on cost of goods. So this is the cost per gram of manufacturing the monoclonal antibody product, but this is normalized because we are interested in the relative cost, so the change in cost as we move through the different iterations of the process. So number 1 is the baseline process, number 6 is the next gen process, and 2, 3, 4, and 5 are the various iterations needed to go from 1 to 6. And what we can see here is that there is a reduction in the cost of goods with each change that we make. Cost of goods are reducing with each change that we make, and overall the reduction in cost of goods between process 1 and process 6 is almost 30% reduction in cost of goods. So let's take a look at process mass intensity. Process mass intensity is a measure of the amount of consumables, materials, and water required to make a product, and this is one of the outputs that Biosolve gives. Here we plot process mass intensity versus for each of the different processes that we modeled, so from 1 to 6, and we can see a general downward trend in the process mass intensity from process 1 to process 6, and this is because with each iteration of the process, unit operations are getting smaller, and the process is becoming more efficient, and therefore we are needing to use less of those things. The only place where you see a slight increase in process mass intensity is between process 3 and process 4, and this is because process 4 goes back to a 2-stage depth filter clarification train, whereas process 3 is the Harvest RC product, which is a single-stage chromatographic clarification. So let's take a look at where the lower MAB costs of goods come from. So Biosolve considers consumable costs, labor costs, capital costs, material costs, and other costs. And these together form the cost of manufacturing a batch. In terms of the capital costs and the material costs and the other costs, those essentially didn't change between the 6 different processes modeled. So I haven't presented them here. What I've presented is consumable costs on the left-hand side and labor costs on the right-hand side. And we can see that these show 2 different trends. So the consumable costs on the left-hand side shows a general increase as we go from process 1 to process 6 in consumable costs. And that makes sense because the technology is getting more expensive because it's doing more in your process. If we look at the labor costs, we can see a general downward trend in labor costs, and that again makes sense. The technology is doing more, and therefore the people running the process need to do less, and so we can see a reduction in the overall labor costs. You will see that these in both cases the bars are grouped into 3s, and this is because the first set of results are for the evolution of the clarification train, and the second set is the evolution of the clarification train with the addition of polisher ST, and the same for the labor costs as well. What's interesting is that when we compare the overall magnitude of the change in labor cost from process 1 to 6 to that of the consumable process cost from process 1 to 6, the magnitude is pretty much the same. So if we look at process 1 to 6 for labor costs, we can see an overall reduction of just under $100,000 per batch. And for consumable costs, we can see an increase of just under $100,000 per batch. So it's clear that if there's no change in capital costs, material costs, and other costs, and the labor and consumable costs cancel each other out, the question then becomes, where do the lower cost of goods for the MAB come from? And this graph really explains where it's coming from. So here we look at the capacity to manufacture your MAB in kilograms per year, and we plot that for each of the 6 processes that we looked at, and we can see that there is an upward trend in the MAB manufacturing capacity. And that means essentially with each iteration of the process where there is an increase in capacity, we're able to produce more monoclonal antibody in our process. and that is driven by the increase in yield across the downstream process. So the yellow bars here, which are behind the peach colored ones, are the DSP yield, and you can see that the yield and capacity overlay each other extremely well. So it's clear that with each iteration of the process, where there is an increase in yield, it is driving that increase in capacity. And again, if we look at the overall magnitude of that increase in capacity and yield, it's of the order of 30%. So it is clear that this is what is driving the reduction in the cost of goods, and therefore the implementation of the technologies that we've discussed in this presentation is essentially making the process more efficient, being able to produce more product with less, and therefore reducing the cost of goods. So overall, we found that there was a reduction in cost of goods of approximately 30% from the next generation approach using the 3M technologies that we modeled in these processes. This was driven primarily by better DSP yield, which increased the MAB processing capacity of the manufacturing facility, and we also found that there was a reduced PMI, which indicates that there are less consumables, materials, and water being used, and therefore less process waste generated. Again, indicating that the process is more efficient. And all of this together, as I said, really points at the ability of these kind of technologies that we examined to do more with less. So before I finish up, I would just like to recommend the following talks to you. The first one is a technology workshop by Alexei Voloshin. It's on enabling new bioprocess strategies using advanced process technology solutions. That's on the 22nd of September 2020, and it's at 12:30 Eastern Standard Time. I'd also encourage you to watch my colleagues' on-demand technology showcases. The first by David Chow on bringing chromatography to cell culture fluid clarification, and the second by Joris van der Velde on enabling transition from column to single-use AEX unit operation. So I'd like to finish up by thanking you for your attention. It's been a pleasure to present this work for you. And if you have any questions or want to reach out to me, please feel free to do so on the email address shown on this slide. Thank you.